Hey everyone, and welcome back to another CTF Writeup video. In today's video, I'm going to be covering the Pwn Challenges as part of ångstrom CTF. Specifically, I'll be covering all the traditional Pwn Challenges. I'm not going to cover the blockchain challenge. I also didn't solve the very last challenge, noleek, but thankfully the author did a official write-up, and so I'll just be showing his solve script. And yeah, it was a fun challenge, so I feel like it should be covered. If anyone has any questions or comments, feel free to either leave it in the comment section below or message me on Discord. If anyone has an easier solution to any of these, please also put in the comments. I'll pin it to the top. Make sure other people see it. And with that, let's get started. The first challenge is queue. It says, I just learned about stacks and queues in DSA. We're given a netcat port and a download file. If we open the download file in Ghidra, this is the main function. Thankfully, it's nice and short. We can see here it's going to open up the flag. We'll call this flag file. Then it's going to read from the flag file OX80 bytes into, let's call this the flag buff. It's going to ask us what we learned in class today. It's going to read standard in OX30 bytes, so we'll call this the in buff. And then it's going to do a printf on our in buff, so here's the vulnerability. Then it's going to say, sounds pretty cool, it's going to exit. So we have just a printf sort of vulnerability. You can't pass user input into a printf. We could look at a buffer overflow and see if it's possible. We can see the size is 48 bytes in decimal, and this buffer is defined to be 48 bytes, so there is no buffer overflow. We're really just going to be doing a printf. What makes this challenge relatively simple is that they put the flag contents on the stack, and with this printf vulnerability, we can just read variables off of the stack. So all we really have to do is just print out the entire stack, and in there our flag should just be there. We can take a look in GDB to see what that looks like. So I'm going to start Ubuntu 22. For doing this Ubuntu stuff, I have another video on my channel. It's called Favorite CTF Tools, where I show how to set this up and create custom Docker files for everything. Most of the challenges on the CTF used Ubuntu 22, so just keeps things simple. So let's do GDB, and it was called queue. We're going to break on main. Let's run it. We're going to do next. I'm going to go until after it reads the file. So now it's doing an fopen on flag.txt. We're going to skip. It's going to do an fgets. And so this is going to read from the flag file OX80 bytes and store it into this buffer. And so I'm going to copy that address. I'm going to do next. And so now we can do an examine string at that location, and we can see it right in a flag. And so we can also check the stack. You can do stack 50. And let's do stack 20 maybe. We can see the flag is right here on the stack. So here's our stack frame. And yeah, these are just other variables on the stack. This is probably our flag file, oxfbad. So this is a file, and yeah, and soon we'll be able to type in, I think this buffer will probably be our input, but like we can see, the flag is just defined right on the stack, so that makes this pretty nice and easy. To read values off of the stack, we can use the printf tool, or printf vulnerability. So what we're going to do is, let's actually clear it, take a look at queue. So we can do %p, %p, and see what it looks like. And you can see we're going to be reading all these different values, which is pretty fun. So all we really need to do is figure out which %p actually corresponds to our flag. We can tell these are not it. 7ff is going to be a stack variable. 7f14 is probably going to be libc. We only get so much input, so if we want to reference a %p that's like further down the stack, you can use the $sign modifier. So we can do %for $p, and so this will actually access the fourth element on the stack and print it out. And we can see the fourth element is a OX9. I think the flag actually starts, so I made a little script that just brute forces all of these. I think the flag starts at like 15 or something like that. We'll look at the solve script in a second. So if I print out the 15th element using %p, oh, oops, did that wrong. %15 $p. We get this. So this is looking better. 31, 32, 33, 7D. I would guess that 7D, oops, man, ASCII. Oh, what's going on? Man, ASCII. If we go down to the hexamal, 7D is a close bracket. So that was probably the flag right there. So starting roughly around 15, we should be able to just grab like 15, 16, 17, 18, and that should print out the entire flag. So let's take a look at the solve script I wrote. What this is going to do is it will, this is just standard Pwn tools sort of stuff. We're importing Pwn, time warnings, I'm disabling warnings. I'm not going to cover this on every challenge. I'll just cover it on this first one. This is how we load the binary. So we say Pwn elf, we load it in. You can set context to make it Pwn tools a little bit smarter about the architecture and bits, 32-bit, 64-bit, stuff like that. I set log level to critical, so there's not too much garbage for this challenge. Since I do everything within a Docker container, I'm using tmux, and so this tells it when you spawn GDB, just to do it in panels, which I'll show in a different challenge. We load libc in case we need it. This is where we're going to store the flag, this out, and then I'm just going to iterate a bunch of times and slowly leak out the flag. We can do it actually, we'll just do it remotely since it's easier. So I'm going to connect to the remote one. After the today, I'm going to send it that %14, and then %p, and then I'm going to do 14, 15, 16, 17, 18. Receive until here, and then I'm going to strip out the rest, and we should just get the flag piece by piece. So we can see what that looks like. Python 3, let's go back into an Ubuntu box. Make Ubuntu 22, Python 3 solve. And there it is. I wonder if we can, actually we'll just do debug. So that was the flag. It built it up kind of quietly. I turned on debug mode to see if we can see what we're actually sending back and forth. We opened up a connection. We received what did you learn in class today. We sent these bytes, so print out the %p, so just hexadecimal of the 16th element on the stack, and this is what we received, this. And so we're receiving hex, but I convert it manually in Python, but I mean you can use CyberChef or something like that. So if we go to CyberChef, we'll paste that in, we'll do from hex, and we can see here's part of the flag, so A-T-I-U. I think it's backwards though, so I think it's probably going to say Q it. What was the flag? Oh yeah, stack it Q it. But yeah, nice. We can just use printf to read variables off the stack. The next challenge is Gaga. This is actually 3 different challenges. The challenges kind of build up on each other. I figure we'll cover all 3 since they're pretty fun. The last challenge came with a Docker file, and the Docker file had 2 interesting things. First off, it's a red Pwn jail. It didn't matter for this challenge, but sometimes red Pwn jails can be a little bit weird. But like I said, we didn't have to worry about it too much. And the second interesting thing is they're basing it off of Ubuntu 2004. So that means if we need libc, which we will need libc, we should make sure we're using Ubuntu 2004. Like I said, there's 3 challenges. The first challenge was Gaga 0. And like I said, they build up on each other, and they're trying to just teach basic exploitation techniques. This first one was a ret to win. So they print out some text, then they do this gets on this in buffer. I think I renamed this in buffer. It was called something else earlier. But this is an unbounded gets, which means that it will keep eating content until you stop. But it only declared a buffer size of 60. So if we were to send more than 60 bytes, we could clobber other interesting things. And that's pretty much what we're going to be doing. There's also, let's take a look at checksec to see what protections are enabled. So we can do checksec file gaga 0, and we can see 3 interesting things. First off, no pi. So if we need to jump to an address, that's very easy because it's going to be at a fixed location. NX is enabled, so we're not going to be writing any shellcode. We're going to be doing a ret to win. We're going to be jumping somewhere, and there's no canary, which makes the buffer overflow easy. And so our target as part of this is to jump to this win0 function. And so this is the win function. All it does is it just opens up the flag file and prints it. So as long as we can jump to this win function, we win. And so, like I said, this is just basic buffer overflow. I'll cover what it looks like in a whiteboard real quick. So what the attack we're about to do is there's a stack. We'll call this the stack, and it has a bunch of entries. There's also the .text segment. So this is where like the program executable memory exists. And so this is usually, for this challenge, it's OX400000, something in that region. And so in this text segment, there's the main function, which we're dealing with. It has all that stuff. And at the very end, there's a ret, and somewhere in there, there's also that gets call. And we'll call that gets of buff. There's the win function. I think it was called win0. And there's also some exit cleanup handler. I'll just call it exit cleanup. Technically, I think it's in libc, but it really doesn't matter. So as part of the stack frame, the very last thing on the stack frame entry is this return address. And so normally, so let's say this is in buff. Normally, like I said, at the very end, there's the return. And so when we enter a function, this return value is saved on the stack. And when we leave a function, we pop off this value onto the stack and start executing there. When we jump into main, it's currently set to some other address like exit or cleanup. Like I think it's within libc, but it's just pointing to some other executable code. When we do our buffer overflow, when we do that gets call over here, we're basically going to clobber all of this. And instead of it returning to the exit handler, we're going to say, nah, I actually want you to return to win0. So we're going to point here. Which is pretty crazy. And so when we do this return call at the end of main, instead of jumping to this exit handler, we're just going to jump to win0, and it should just print out the flag. And to see what the solve script look like, let's go over here. This is it. Same sort of Pwn tools, same as every challenge. I start the process. For this one, we need to calculate something first. We need to figure out how much input it takes to get to that return address on the stack. A very simple way to do this is to use Pwn cyclic. And so what this will do is it'll send a cyclic pattern to the process, and you can inspect it in GDB to see at what offset you overwrote the return address. And so you know how much input you need to send to get to that return address. So to see what that looks like, hey, interactive. I'm going to attach GDB. I'm going to send that cyclic input, and then I'm going to pause the process so we can take a look. And to do that, we need to be in a tmux, python 3 solve 0.py. So this is that giant piece of input we sent. We can see it's just a nice clean pattern, AAA, BAA, CAA. And when we hit continue on GDB, it should crash. And we can see it's crashing right here. This looks really messy, but basically it's saying it's trying to return, but it met some weird ASCII characters. And it didn't know how to return to that address, which is exactly what we want. It means we were able to do the buffer overflow. And those particular values are SAAA. So this is probably AAAS. So perfect. We can take that and use cyclic find to figure out what value that is. So we can actually print it out. You can do f offset equals. We no longer need this. We're not going to send that. And I guess we don't need it really. Actually, we'll keep it. We'll just print it out. We'll go here, and let's see what that value is. So we have to offset is equal to 72. That means we wrote 72 bytes, and the bytes that follow that overwrite the return address. Cool. So for our actual exploitation payload, so what that means is we are going to send a bunch of A's. This is just filler. We're filling up the buffer on the stack, and we're going to send offset -8 of those. Technically, we'll just do a full one. I just did that just in case. We'll keep things simple for now. So we're going to send all of those, and then afterwards we get to put that win address. Thankfully, it's nice and simple. We have that elf. Pwn tools will parse out functions and stuff for us, and we can just say, hey, Pwn tools, give us the address of win0. And we wrap it in p64, just because we know it's a little endian. And then we do p interactive, and we should just get the flag. So let's cancel that again. Python 3 solve 0, and there we go. I'm using the local flag. We can get the remote flag. Cancel that. And here is the start of the remote flag. Like I said, there's 3 different challenges, so we only get little pieces of the flag. But yeah, that was a basic ret to win buffer overflow. Gaga 1 was pretty much the same. There's just one little difference. It says now you need to call the win1 function with the correct arguments. But we get the same sort of buffer overflow. There's a local buffer with size 60, and we're doing an unbounded gets on it. If we take a look at the win1 function, we can see it's a little bit different. It's still going to read the flag and print it out, but the difference is it's doing this if condition check for param1 and param2, and it has to be equal to elite and 4141. We could try to do this if condition, or we could just cheese it. Like, you don't have to jump to the start of the function. Instead, we could just jump here. Like, when we do that jump, we're just specifying an address. So there's nothing stopping us from jumping just to this part of the code that's printing out the flag. So if we take the address right here, I just click on this line. I'm going to copy this out. So this is 401269, and we'll place that in our solve script. So this is the solve script for challenge 2. And we can see we already have it right here. So OX 401269. The rest of the solve script is pretty much the same as the last challenge. All the same stuff. Here's the remote. We do the Pwn cyclic find. I think the last one was also SAA, so it's the same. There's one other difference between this challenge and the last challenge. So the last challenge, we didn't talk about it, but on the stack frame, the stack frame stores both the return address and it also stores the base pointer. And that base pointer goes into a register called RBP, and that's useful because you don't necessarily know how big a stack frame is going to be for a particular function, and this is just a way to jump back to your previous stack frame and kind of keep everything nice and clean and aligned. The previous challenge never referenced anything off of RBP, that base pointer, but the win function on this one does, and so we just need to make sure that we don't clobber RBP. It's very easy to do. We just need to be careful, and we can see right here. So this is that win function. I'm sorry if this is small, but basically this is just accessing RBP. In the previous challenge, since we just overrode that RBP value on the stack, it would be OX41, 41, 41 or something like that. When you try to access it, this memory address using OX41, obviously the process will crash. There's nothing at OX41. So what we do is we just set it a random value that is both readable and writable. Since pi isn't enabled for this challenge either, all ELF binaries usually have a space that's both readable and writable. We just pick a random address in there, and so that way we know we're safe. To find what one of these addresses looks like, you can go to GDB. This is gaga 1. We can do break main. We'll do run, and then we'll use the VM map command. And so this is where you can see all the different sections or segments. I get the two of them confused. But if we scroll down, this is our main gaga 1 binary. So this is our read and execute. So this is probably where the main function and all that stuff exists. And we can see here, this has the read and write permissions. And so we can read or write to any memory address in here. So 404 to 405. I just pick something right in the middle. So I do 4045. And that way we know, if the stack's going up or down, it really doesn't matter. So 4045. And yeah, that's the only change we had to make for this one. So Python 3 solve, 1.py, and we get the flag, ACTF baby's first pwn. Like I said, otherwise everything was the same as the last one. The final Gaga challenge, Gaga 2, was definitely a little bit of a step up compared to the other ones. It went from, you had to use a new technique. So if we look, let's actually first load it in Ghidra. Don't save, Gaga 2. We'll go to functions, main. Cool. It says awesome. Now there's no system. So what will you do? There's a printf and another unbound gets. Cool. I'm a little bit confused by this message. I think maybe it's saying that there's no more win condition. But basically, there's no ret to win. There's no function that we're going to jump to that'll automatically give us the flag. And so we need to kind of create our own function that'll get us the flag. Like I said, this challenge, this last one is definitely a step up in difficulty, and it's a little bit more involved. Let's also take a look at checksec, make sure nothing else changed. So make Ubuntu, we'll do a checksec file, gaga2, and it's the same protections. There's no pi, so we can jump anywhere in the main elf, but we don't know where libc is. We'll talk about that in a second. Still non-executable stack, so we're not going to be injecting shellcode, and no canary, so we can still do our buffer overflow. So again, taking a step back, what's different about this Gaga, this new Gaga challenge is there's nowhere immediately obvious where we would want to jump. And I think what this challenge is saying is that you need to jump to system. And so what makes this a little bit trickier is system. So you can run system commands, you can run bash commands. Once you're able to run bash, you can print out the flag. System exists within libc. And so if we do GDB, let's run gaga2, break main, run VM map. So libc is here, and somewhere in libc is that system command. What makes this difficult is we need a info leak. We don't know where libc actually exists. Like right now it has address 7fe75, but if we were to run it again and do VM map, now it's 7ff9b. Every single time it's going to change. And so what we need to do is figure out what this address is. Once we know what the base of libc is, we are able to jump to the correct system location, but it's we first need to leak that address. Again, there's another complication, and we're going to have to write wrapping code. So let's talk about wrapping code. Let me scroll down. So I'm going to draw pretty much the same thing. So we're going to have a stack. And we're going to have that return address that we're going to clobber. We have our in buff. Cool. So we have our main gaga 2, and in here, we have the main function, and that's pretty much it. There's no ret to win function. It's going to have its ret. There's something called a global offset table in here, which we'll talk about in a second. And then we also have libc, which is at some, OX7F, some unknown address. Cool. And we're going to be writing ROP code. So it used to be like, 10, 20 years ago, you used to be able just to write instructions onto the stack. And so what would happen is normally you'd have this in buff, and you would actually write raw assembly in the in buff here, and your return address would jump right straight back to the assembly that you just provided, and that was called shellcode. Unfortunately, or fortunately, I mean, we're good guys. Fortunately, you can't do that anymore. And so instead we have attackers and CTF players and stuff have to be a little bit more clever. And the cleverness that people now employ is called ROPing. And basically what we're going to be doing is we're going to be using existing code gadgets that already exist within the binary. Cool. And the way that looks is, so there's this ret call. It's a very powerful item. What ret's going to do is it's obviously when we call ret in the main function, it's going to start executing here. And if this thing, this code, like let's say there's another function like, I don't know, let's say func2. This doesn't actually exist, but func2, let's say it does a pop RDI and then a ret. If we were to return to this right here, it would start executing these commands. The next command's a pop RDI, so it would actually just take the next value on the stack. We'll just call this RDI, and it would set, it would pop this value off of the stack and set that to RDI, and then next it would execute return, and so it would just read the next value on the stack and return there. And so, this could go, some other code segment. These little things right here are called gadgets. There's a whole bunch of them in every binary. Basically, we're looking for something that does something interesting and then is followed by a return. There's other type of gadgets called jump gadgets and stuff, but basically this is really what we want. I mean, these are the good gadgets. And so you're going to look for gadgets that, modify a register and then immediately return. And technically this is not executable code that's going on the stack. This is just, data, but it's telling the processor, go here, execute this code. Here are your variables. We're basically able just to call a bunch of different functions. Super powerful stuff. Cool. Like I said, this challenge is definitely a step up compared to the previous two. So anyways, that's ROP coding. We still need a info leak. There's, again, this technique. I feel like when I first heard about this technique, there was no way I would ever figure this out by myself. But now that you know what it is, it just gets used all the time. So anyways, within a process, there's a thing called a global offset table. And this global offset table is a mapping between functions and where they exist in memory. And so what's going to happen is, this is a very deep subject, but the gaga binary, it uses so the challenge authors, they gave us the gaga2 binary, but they didn't give us libc. But somehow we're still able to execute the gaga2 binary. And that's because the gaga2 binary is using the libc on our host system. Everyone's executing this gaga2 binary and they're all using the libc library that's on, all of their respective systems. But people are going to have slightly different libcs. And one way this works, and libc is constantly being updated, there's patches and stuff. And what happens is, there's this linker or loader sort of process. What it's going to do is that when it starts spawning this process, it's going to fill out this table called the global offset table that kind of tells the gaga binary where everything is loaded in memory. And so the global offset table within the process, it's going to have an entry for printf, and it's going to say, oh, printf is located at this address. So, within libc, there's going to be the printf function. And it's just saying, it is right here. This is just, some data that exists within a process. It's very useful for an attacker because if we could print out this value, it would tell us where printf is. And if we know what version of libc this process is using, we can then calculate the base of libc, and then from there we can calculate where system lives within libc. Cool. So what we want to do is actually print out this value on the global offset table. The way we're going to do that is we're going to find a couple of gadgets. Technically, Pwn Tools is going to find these gadgets for us, but we're going to look for a gadget that does a pop RDI, and we're also going to do a pop RDI return. We're going to put this value. This is at a known address. It's going to be like OX 404020 or something like that. We're going to put the value of printf right after our RDI, so it's going to go here. So first we're going to call pop RDI return. We're going to put the value of printf on the stack too, so it's going to take this value here, and then after we do this gadget, we're actually going to call puts. Somewhere also in here, there's this other thing called a PLT. Not too exciting, but basically there's a piece of code in the existing binary that will jump to puts and start executing puts. And so when we set this value here to RDI, puts will then just print out this value for us. So we're going to call puts on the value of printf. Again, it sounds a little complex and weird, but once you get used to it, it's just a very standard technique you do over and over. Cool. So yeah, like I said, we're going to print out that value, and once we have that value, we can calculate the base of libc. This is called our info leak, and from there we can start jumping to system and doing fun stuff. Cool. I think that's it. Oh yeah, so we need to execute this function twice. So at the very end, we're going to call puts. We're going to print out the value of printf. We could print out any of the global offset table entries. There's printf, there's going to be exit, there's probably puts, read, write, a bunch of different things. We can print out any of them. I just picked printf. And at the very end, we're going to jump back to the top of the main function so that we can execute again. I don't think, we technically need to do this gets call twice. And so once we're all done, we're able to return anywhere we want. And so we're just going to return, the final ret will just be right back to main. So recapping, first we're going to leak libc. We're going to do that by calling a bunch of these little gadgets. We're going to pop RDI, we're going to place this value on the global offset table, then we're going to call puts on it, we're going to print it out, then we're going to jump to the top of main, and that's our first ROP. And then in our second ROP, we're going to find a value of bin shell. Technically the string bin shell actually exist within libc. So we're going to find where that value is within libc, and then we're going to call system with bin shell, and we should just have shell in the system. And to call system and bin shell, again, we're going to be ropping. Thankfully, Pwn Tools does all the ropping for us, but it's good to know how it works. And sometimes you do have to do like raw ROP code, raw ropping yourself. Yeah, so let's take a look at the solve script. Actually, while we're here, let's take a look at the global offset table. So I'm running gaga 2. You can do GOT, global offset table, to see what it looks like. And this is it. So at this address, actually, let's look for printf. At this address, 404030, it contains the value 401060. Actually, let me go next a couple times. Okay, now let's look at the global offset table. There's a minor thing. The global offset table only gets updated the very first time you call a function for a partial railroad binary. It's not too exciting. But basically, now we can see printf has this value here. And so this is our libc leak. So if we were to call puts, print on this printf entry, we would get out this value. And this is exactly what we want. Like I said, this is just a global offset table. It's just a mapping from function to address. Cool. Yeah, I think that's it. Oh, and there's one other tool that will probably come in handy in the future. It's called Ropper. So you can do Ropper, and it'll print out all gadgets. So if we were to construct these gadgets by ourselves, this is what they look like. So I called Ropper file gaga2, and we can see here is exactly the gadget we would want if we were to do it ourselves. This is going to pop RDI and then hit return. And so using these gadgets, we can do a lot of very clever and fun stuff. Anyways, let's look at the solve script. So this is solve2.py. So this is the same sort of stuff. Again, doing a Pwn cyclic to figure out what that offset is. It was the same offset. And this is our first ROP code. Very exciting. So we're going to do a pwn.rop. We're going to load in the elf. And we're going to say, hey, ROP code, call puts on the global offset table entry for printf. And so that'll give us a leak. And then we're going to jump back to the top of main. So we send that over, p send line, same sort of stuff we saw in the other exercises, and we send rop.chain. So like I said, this is going to build out the ROP chain for us. We can actually do rop.dump. I think we need to print it. Cool. Then we're going to receive that libc leak and parse it out. So I received the line, I printed out just to make sure we're doing everything correctly. I'm going to unpack the value. So this is the libc leak. I think it's only going to be 6 bytes. So we justify it to 8 bytes with some null bytes, just to, you know, make all the tools happy. Then we do a Pwn unpack, and this should be our libc leak. From there, we calculate the base of libc by taking our libc leak and just subtracting the value of libc symbols printf. By default, libc symbols will reference start at 0 because we haven't supplied a libc address. So this will start at 0, and so this is just the offset from the base of libc. And then I print it out just to make sure everything looks correct. It should end in 000 if we did it correctly. And then the next step, now that we know where system exists within the process, we're going to build a second ROP chain. And so we're going to do Pwn ROP with libc. This is a annoying thing, but it's something that we have to do now. On modern versions of libc, they expect the stack to be aligned to values of 16. And basically what that means is sometimes if your stack address, your RSP, ends in an 8, certain assembly instructions just won't work and the process will crash. And so basically you just have to make sure your stack variable ends in a 0 when you call certain instructions. libc, if you're using libc correctly, like it'll always ensure that that happens. But since we're kind of jumping around and cheating a little bit, our stack gets a little bit wonky and it ends at an 8. Our stack variable ends at an 8. And when we put this return address, basically it's just like a no-op instruction. It doesn't do anything. It just jumps to the next entry. And so yeah, that way our stack variable ends in a 0. Again, it's silly. If you ever see like it's like some XMMA instructions or something like that, that's what that's about. Anyways, then we're going to say ROP call system with the string, find the address of bin shell, get the first value, and then call system on that thing. And so this is going to do that pop RDI stuff for us. Amazing tool. Let's copy this out so we can view it. And then we send over that ROP chain, and at this point we should have shell. So let's take a look and see what this looks like. Python 3, solve2.py. Cool. So this was our first ROP chain. So we see it's a pop RDI return gadget. Then it's going to set the global offset table entry for printf on the stack. Then it's going to call puts, and then it's going to call main. So cool. So this just builds out that chain for us. Then we send it over. You know, we can see we got a whole bunch of A's. This is our ROP chain. Here's dead beef for the RBP. You know, a bunch of entries, and then it exits. Then we read in a bunch of stuff. We build out the second ROP chain. We should be printing out libc somewhere. Oh yeah. Yep, this is the value, the data we received. So this is the raw value for printf. This is that leak once it's parsed, and this is our new libc base. So from here, we can build our second ROP chain. So we have 7f, 69, blah, blah, blah. We pop another RDI. We load the value for bin shell. Then we call system on it. And from there, we should just have shell. I think I waited too long, but we can see we have shell and we can cat out the flag. Baby's first Pwn. Like I said, definitely a step up from the previous two. Required a little bit more knowledge, but super useful stuff. If you didn't get it your first time, really no worries. It took me like doing a whole bunch of these binaries to understand it, but very useful techniques in this challenge. Sweet. The next challenge was leek. This is my favorite Pwn challenge. We're given a Docker file and the download binary. In the Docker file, again, it tells us we're using 2204, so we just need to make sure we're on Ubuntu 2204. If we take a look in Ghidra, there's a little bit of code. Basically, just before we jump into the code, what's going to happen is the binary is a little bit contrived, but basically we have to guess some random numbers. And the way it's going to work is we need to pass 100 rounds, and the program is going to generate 2 buffers on the heap. We get to input into the first buffer, and the second buffer has 20 bytes of randomness. And like I said, we need to guess that randomness. And the trick to this one is that we're actually going to overflow that heap buffer such that when we do a print on our buffer, it's going to keep reading until it hits that null byte. And since we did an overflow, we can make sure that those 2 heap chunks are continuous with no null bytes or new lines, and it'll print out everything. Then it's going to free both of those buffers, and when we do the freeing, we just have to make sure we're going to do another heap overflow, and we just have to make sure we change back the heap chunk so it's like a valid heap chunk, and when we call free, everything works correctly. So pretty fun challenge. It's like a very good beginner sort of heap exploitation challenge, although again a little bit contrived. But anyways, that's pretty much the challenge. I'll just go quickly over this. It says I dare to leak my secret. While true, we can see this is the rounds, so we'll just call it rounds. while rounds is less than 99, looks like, oh, if rounds is greater than 99, it calls the win function. This just prints out the flag, nothing too exciting. Like I said, it's going to malloc 2 buffers. So we have one, this is 16 bytes, and this is 32 bytes. We'll call this, I don't know, buff1, and buff2. It's going to memset buff2 to all zeros. And then for buff2, the same thing, the same buffer, it's going to set it to a bunch of random bytes. Again, like I said, this challenge is a little bit contrived. To make sure this works, there can't be any null bytes or, I guess, new line statements in buff2. Otherwise, when we do our little print and we try to, print past the bounds we're normally supposed to be allowed to, it would exit early and we wouldn't be able to guess the randomness. So a little bit, contrived, but still fun. So anyways, it's going to print out, it's going to say no stack buffer overflows because technically we're doing a heap overflow. It's going to read input, and then it's going to tell us what our input was. And this is just, just reading input. There's nothing too exciting about this one. And then it's going to ask us what the secret is. It's going to read in OX21 bytes. So this is our we'll call it in guess. And then it's just going to do a string compare. And if we get it correctly, we get to input some more input. And this is so we can unset that heap overflow because we are clobbering it. And then it's going to call free on both buffers, and we should be good. So just taking a quick step. When we look at the heap, again, there's nothing really magical about the heap. It's just another place where we can assign variables and stuff. Heaps, they're going to be located somewhere else in memory. They're not going to be located next to like the main elf. They're not going to be in the stack. They're their own memory address. When you request something from the heap, usually you use malloc, but there's other functions. The thing you get back is called a chunk. Chunks can take a variety of different forms, but for the most part, it's just going to have a size buffer. So each one of these is a little chunk. So there's a size, and the rest is contents. There's sometimes like there's like 8 bytes before and forward pointers and backward pointers and all that stuff. For this challenge, we really don't have to worry about any of that stuff. All we really care about is the size and contents. And so what's going to happen in this challenge is this is going to be our input buffer, input, and this is the random that we have to guess. Sorry for my sloppy handwriting, but I'll do a little bit better. Random. Cool. So we get to do a input on this. I can't remember if it was gets or read, but we get to fill out this buffer. And what we're going to do is we're actually going to overflow this with, A all the way through, and we're going to overflow past this too, so that the next byte is the start of the random bytes that we have to guess. When we call puts on this, on our input, puts will continue, or printf, I forget which one, I think it was a puts. Puts will continuously print out character by character until it either hits a null byte or a new line. And since we were able to clobber all of this, and none of this content contains a null byte or a new line, puts will just print out all of this, which is great. We'll get out the random bytes. When we call free on a buffer, malloc needs certain things to be true. Again, it's going to check the size field, and there's other information in the size field. Again, it's 8 bytes, but there's like a previous in-use check and some other stuff that's not important for this challenge. We just need to set the size field back to what it's supposed to be. Otherwise, when we call free on it, malloc and the heap are going to be mad at us. So what we're going to do is we're just going to set on the second iteration where we get to send another buffer. We're just going to fill up this buffer. I think we just send null bytes. Maybe we send content, and we set the size back to what it originally was. I think it was just OX20 or something like that. Maybe OX21. And yeah, as long as the size buffer is correct when we call free, the heap is none the wiser that we just did all this heap corruption, and the heap will gladly free these buffers, and we can continue. And we pretty much just do this 99 times. This act of overflowing the heap buffer, printing out the random bytes that we need to guess, and then fixing the heap corruption and continuing. And at the end, we get the flag. To see the solve script, it's nice and simple. We have the process, we have the remote, and for 99 rounds, we're going to send a Pwn cyclic of 32 bytes minus 1, because we have to send a new line too. Not too exciting. And that'll clobber everything. And then we're going to receive that line, and then we're going to receive the 20 bytes of randomness, since puts is going to print out all of that interesting stuff for us. Then we will print out the leek just to see what it looks like, and then we send the leek right back to the process because it's going to ask what is, my random bytes. And then after we're done with that, we need to unclobber that chunk. So we're going to send it OX 18 bytes, and then after that, I guess we send it an OX 31. To kind of see what all this stuff looks like, so we'll run gdb leek. We can break on main. We'll run. I'm just going to call next a whole bunch. We'll skip forward. Next. I'm waiting until it looks for input. Main. Oh, I think it's right now it's reading in a bunch. We'll skip all that stuff. Let's jump on, maybe break on printf. Break printf. Continue. We'll finish. Then we'll do a next. Oh, it wants our input. We'll say hello world. And yeah, let's see what the heap looks like. So there's a very useful command in Pwn debug called viz heap chunks. Just beautiful command. And so this is what the heap looks like. We can ignore the stuff up here. It's not relevant to the challenge. And these are the 2 heap chunks that were created. So this heap chunk is the random bytes that we're trying to guess. I can make it a little bit bigger. The random bytes that we're trying to guess. And so we can see there's 32 bytes here, just pure randomness. And this was our input buffer. We can see it says hello world right now. And you can see it's a little endian, so it's a little bit weird, but you can see these are null bytes, but technically all of this and this is the hello world. And this is the new line right here. And yeah, like I said, what we're going to be doing is we're going to be overflowing. So instead of just writing hello world, we're going to write all of this with content. And that way when we do the print starting here, it'll just print out all of this because the puts isn't going to encounter a new line or a null byte. I think it's just null byte. I think puts can do a new line. Yeah, that's pretty much it. So we can run the script. One thing we had to do, we did need to check this the first time I was writing the exploit. We needed to see what value we needed to set this to when we were done. So when we unclobber it, we're going to send some content here. I think we send nulls. No, we don't. I just clobber all of this, and then I set OX31 here, and you can see this here in the solve script. And yeah, that's pretty much it. So we can run it, Python 3, solve.py. It's just going to, again, read the values, print it out, send it to the process, and after it runs 100 times, we should get out the flag. And there it is. Very leek of you. So very cool challenge. The next challenge is widget. It seems I seem to have lost my gadgets. We're given a netcat port, the binary, and a Docker file. If we look at the Docker file, we can see it's using Ubuntu 22.04. So that'll be useful. If we open up the binary in Ghidra, I already renamed some variables, but just going through, it's going to do some buffering and stuff. There's going to be this global variable called called, and so we're only allowed to call main once, because if called is not equal to 0, it'll just immediately exit. It'll printf, it'll ask us for a size. We can see this isn't rendering correctly, it's just doing that dat thing, but if you want to change it and so it like parses correctly, you can go here, you can right click, we're going to change data to a terminated C string, and now we can see it's doing the %d correctly. But it's going to read in a number, a %d, and that'll be our in size, and then it'll read in that many bytes into this buffer called inbuff. And up here is inbuff, so the buffer is 24, and we can read in whatever we specify. So obviously we have a buffer overflow, that makes that easy. Then it's going to do this, the code looks a little bit confusing at first, but basically what this code is going to do is it's going to loop over every character and make sure the character is not equal to n. So we're not allowed to have any n characters. As long as every character is not equal to n, it'll eventually do a printf on our buffer, and then it'll return. So at first, I made this way more complex. During the CTF, I made it way more complex than it needed to be. Right before recording this video, I went back just to refresh myself on the challenge. I didn't realize there was a win function here, and that makes this challenge trivial, like one of the beginner challenges we just did earlier. Bits of the swin function, it's going to do a string compare against all this stuff, and if as long as we pass those checks, it'll open up file and print it out. But again, we can employ the same trick we did earlier. We don't have to start at the start of the function. We can just jump right here. And so we could jump to this address instead, and it'll just print out the flag. If we do checksec, so checksec file is equal to widget, we can see there is no pi, so we are able to just, we don't need an info leak or anything as long as we're in the main widget binary section. So yeah, this challenge is absolutely trivial. All we're going to do is we're just going to do a buffer overflow and then jump to that win address. So this is the solution. I'll cover the other solution, what I actually did in a second. It's going to look similar to the other challenges, but this particular challenge had a proof of work. So if you netcat to this port, so let me just copy this over. Netcat, and then it was port 31320. You have to do a proof of work. Someone else in Discord was asking what this is about. Basically, this is a way so people don't brute force the server. Basically, you have to give the solution to this challenge, and then you can actually execute it. And basically, it's usually just calculating a hash or something like that. You don't actually have to know how this works. Basically, you just run this command, curl this and then this. Technically, you shouldn't be blindly executing stuff with shell, but we're just going to trust that everyone's doing or being polite, and you get back this response. And so if you pass this response back, the actual process will start. And so then from there we can specify 100 or 10 or whatever, and we'll send some contents, and that's it. Cool. Yeah, but like I said, since we can just do a buffer overflow, we don't even care about the printf. We'll just do a standard buffer overflow and return to that win function. And so that's what I ended up doing. I say the amount is OX 100 bytes, so then I send the offset. Again, I calculated this offset by doing the same sort of thing where I do a Pwn cyclic. I think I saw that it was 40, so I just saved it. We need to set a readable writable section for the base pointer, RBP. So I just do 40500, same as we did in the previous challenge. And then this was that win address. I just put it there and it should just work. So Python 3, solve. This is solve2.py. The proof of work takes a second, which is the whole point of it. Like, it should be computationally expensive. And then afterwards, we send over that payload and we get back the flag. So it was a pretty late challenge, and it only had 64 solves. Oh, sorry, 116 solves. So I'm not too sure why. I'm guessing other people, including myself, made it more complex than it needed to be. Like I said, this is not what I did during the CTF. I just saw this a couple minutes ago before recording. During the CTF, I didn't use any new techniques. We've seen all this stuff before. So to actually solve it, instead I did a libc leak, and then I ropped and did a bin shell, same as other challenges. To get the libc leak, since this was a printf exploit, I just used a bunch of %p's. So like if we go back, we can just run widget. We can say 100. We'll do %p's, a whole bunch of them. And one of these should be a libc address, like this one right here. So this is a OX7F5, so this is probably somewhere in libc. This is a stack address, so we can just copy this one out. That's our libc leak, and then from there we can rop and get shell. So nothing really too special about this. So like I said, step one, this is this solve script I actually did during the CTF. Step one, print out a bunch of addresses. I do done just to make sure I fill up 40 bytes. Then I set an RBP, just to garbage since we don't really need it, and then I jump back to the start of main. We have to be a little bit careful at where we jump into the main function. If we jump to the start of main, since called is set to 1 the second time we execute it, it'll actually get tripped up here and call exit, which is not what we want. So instead of jumping to the start of main, we'll actually jump right here. So 4013 D9, which is what we have here, 4013 D9. So once we've done that, we'll get back all of these %p's, which will have our libc leak. We'll print it out. We'll take one of the libc leaks and we'll calculate this offset. So whatever we leak, that address is going to be going up and down, but it's always a known offset from the base of libc. And all we really care is what the base of libc is. And so this was just some leak from one execution. And during that execution in GDB, I called vmmap to get what the current base of libc is. And so I know every time we get this libc leak, it's going to be this far away from the base. And so obviously you can swap these out with different values. We need to make sure the difference is always the same, which it will be. I print out the libc address. This should end in at least 3 zeros, and that way we know we have the correct base. And then after that, we're just going to rop again. So I send, again, a big amount, OX100. I build another rop payload, this time with libc. I call exec VE with bin shell. And then, yeah, we just send the rop chain and we should get shell. So we'll do Python 3, solve.py. We're going to do that proof of work again. And and it wasn't happy. Oh, bad 74. I think it's possible that there might have been an N in the address. It's not the most reliable code. Yeah, that must have been it. Cool. And we should have shell, and we do. So we can cat out the flag now. You found a useful widget. So pretty fun challenge. Definitely the other way was a lot easier, but this is more of a traditional sort of CTF Pwn style of way of doing things. The next challenge is Slack. We're given the binary, a Docker file, and the netcat port. The Docker file, it just says that we're running Ubuntu 22.04, so good to keep in mind. Eventually we will need libc. If we take a look within Ghidra, there's a little bit of code here. Really, most of this is not important. What's important is there's this loop, and as part of this loop, it'll read in oxe bytes from standard in, and then it'll do a printf on it. So basically, I guess there's a story behind it, you know, it's a Slack app, but really all that really matters is we get to call printf 3 times with a buffer size of oxe, which is 14, like I said, 3 times, which is pretty fun and pretty challenging. We're going to have to use some new printf techniques to be able to exploit it. But basically, spoiler is we're going to be able to change this I variable to something very, to a large negative number so that we can actually exploit this printf multiple times. And once we do that, we're actually going to be writing our ROP code byte by byte. And eventually when we hit return, we'll execute that ROP code and jump to libc and do all that stuff. But like I said, we need to learn some new printf techniques. So the new techniques, if we start out with a normal %n printf that we normally do when we're exploiting printfs, it looks something like this. Normally we do a printf, and we're given some value. We normally, when we do a %n exploit, so %n will take a variable on the stack, and it has to be a pointer variable, and it will write the number of bytes written so far into that variable. And I think one thing that's commonly confused is it needs to be a pointer variable. It doesn't write it to the stack, it writes it to that pointer variable on the stack. And so normally what we do when we're doing a %n is we actually supply that address as part of the printf exploit. So we'll do, you know, ox7f, ox66, you know, whatever the address is, 63c, you know, all 8 bytes of address. That'll be the address. And then part 2 of the exploit is we decide how many bytes we want to write to that thing. So then we'll do a %, you know, 50c. So this is a width modifier, and so this will write out 50 bytes. So technically we've written 8 plus the 50c, so you know it'll be 58 bytes. And then after that we decide where we want to store that variable. And so we'll do a %, let's say this is address or offset, I don't know, 6 $n. And so this is saying write the number of bytes written to the 6th value on the stack. And so we have to figure out which offset this is. You know, it could be 4, 8, 6, something in that range is normally what it is. And it'll write the value to this pointer. Cool. So that's normally what a printf %n exploit normally looks like. There's a couple of variations. So %n will write a 4-byte integer to that address. You can also do, so there's %n, which is normally 4 bytes. Maybe in some cases it could be 8 bytes, but I'm not sure. I think it's normally 4 bytes. There's also %hn. This is 2 bytes. And there's also hhn, which is a single byte. So these will be useful. Cool. Like I said, we only get to supply a buffer size of oxe, which makes things a little bit tricky. You can see this is 8 bytes by itself. This is 1, 2, 3, so 4 bytes. This is another 4 bytes, and then 5, 6, 7, 8. So you know this is 16. Unfortunately, we can't use this strategy. But there's a sneaky technique we can use. We can reuse existing pointers already on the stack, and that's how we're going to be exploiting this. So if we draw out the stack, let's scroll up. We have a stack. There was that loop index. I'm going to put that here. So this is just I, you know, it's either 0, 1, or 2. There's going to be a variable here. We're going to say that this has a value of ox7ff, something like that, and a value here, ox7ff, and we're going to put a value here, and we'll say this is ox7f3. Cool. So this is our stack. And let's cover the exploitation process. First thing, like all challenges, we want info leaks. So first thing we're going to do is we're going to get a stack info leak and a libc info leak. And so to do that, we're just, I think it's like %$1 $P, and I think we use 9%, $9 P. And so that'll leak, let's say this variable and this variable. And so we'll have like I said, a stack leak and a libc leak, and from there we can calculate the bases and other variables. With that stack leak, we're going to calculate the addresses for a couple different things. At the very bottom, there's going to be a ret. So this is the thing that's going to be popped off the stack and set into RIP and continue execution. Eventually we want to write ROP code down here. So we are going to calculate the address of this, and once you have your stack leak, you just subtract like 20 or add 30 or something. If you just play in GDB, you can calculate these values. We need that one. We also need the address of this I. So we're going to be changing this I, and we need to calculate its value. It's going to have a value. It's going to be like OX7FF blah, blah, blah. And specifically, we're very interested in the last 2 bytes of this value. We can say maybe it'll be like 4096 or something like that. So that's this address right here. So 7FF blah, 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 4096. Just made up value. Cool. So step 1 was the info leak. Step 2, we need to find, like I said, we can't pass addresses onto the stack because there just isn't enough input buffer space. And so what we're going to do is something sneaky. We're actually going to find a variable on the stack that's pointing to another stack variable. And so let's pretend this one is pointing here. This does exist on the stack somewhere, but we have a stack pointer that's pointing to somewhere else on the stack. If we remember, when we do a %n, it's actually taking in a pointer. So we're going to do a %n on this stack offset and change the last 2 bytes right here such that instead of pointing to this address on the stack, it actually points here. Cool. And so what this kind of looks like is like we have our info leak and we know where I is. If we take I and we actually do an and we grab out, so this is an ampersand, and we grab out the last 2 bytes. We'll grab out the last 2 bytes of this I variable. We'll put that in a %C. So it'll write out that many bytes, that many values. So, in this case, it would be 4096, that many bytes out into the stream. And then we're going to do a %. Let's say this is offset, I don't know, 12. We'll do %12 $HN. Cool. So it's going to take this offset, write it to this pointer. And so now this will point to 4096. And so it's going to point here. Cool. And so now we have a pointer to this address. We can start writing values to I. We have something on the stack that has the address of I. There's one other little complication. We're going to change I so it's a large negative value. And to do that, to make a negative value, what matters is that first bit, the sign bit. So we actually, and I is a 4-bit integer. Instead of actually pointing to I, we're actually going to point to I plus 3 because we want to write that high byte. So it'll actually, be pointing here. So this will be I plus 3, and then we AND it and we grab the last 2 bytes. Yep, so that was step 2. And then step 3 is we just want to write 255 or any value that starts with a 1 to this I variable, so it's a large minus number. So we'll do like a %255 C %. We'll say this is offset 14. Then we'll do $14 HN. So now 0, 1, 2. This will now be a F, and it will be a very large negative number. So just to recap, we're going to write 255 bytes, and then we're going to store that into the pointer pointed by address 14. So this is 14. It's pointed to I, and we're going to write FF right there. And so now we get a whole bunch of printfs. Cool. Now that we've done that, we can start stage 2 of our exploitation. We have a libc leak, so we can generate a ROP chain. We're just going to call system with bin shell, nothing special. That'll take maybe like 20 or 18 or 16 or 24 bytes. Actually, probably more like 24 or 32 bytes. And to do that, we're going to do a very similar technique to overwriting this I with FF. Instead of writing to the I variable, we're going to start overwriting our return. So very similar. We know what the return address is. This might be, like 5050 or something like that. I don't know. Actually, that's probably not a good one. It could be. It's in hex. 5050. We're going to set it to 5050. Then we're going to write a single value. So instead of writing in like 255 like we did for that, maybe the first byte of our ROP code is like 66. And so, we'll write 66. It'll go into address 14, and we'll write 66 right here. Then we'll increment this by 1. We're just doing a +1, very similar to the code that was over here. Instead of writing I, we're doing it with the ret adder, return address, plus this is the next index, so we're doing a +1, and we'll ampersand it, and we're only grabbing the last 2 bytes. We'll point this, one more, and then we'll do this line here. We'll write a single byte, then we'll increment to 2 over here. We'll write another byte. This will go to here, and we'll just write byte by byte. We'll write out all the shellcode. Oh, sorry, not shellcode, ROP code. And then once we're done, we have our whole ROP payload written onto the stack. We'll delete this, instead point it back to I, and we'll set I to a large positive value. And that way on the next iteration, it'll exit the for loop and call return. And from there, our ROP code will be executed off the stack, and we'll get shell. I think the actual values, like, the 12s and 14s and all the numbers, they're not really too important, and I'm not going to cover them in the solve script. I think as long as you understand this idea, that's what's important. And I think getting the actual values is kind of boring. You just sit in GDB and grab them yourself. But this is what the solve script looks like. The first thing I did is I used this code. Basically, this is just going to go over and print out the stack for us and the different offsets. And I use that just to see how the stack is aligned and look for leaks. So we can see I ran it, and we can see the first stack index. So if I was to do %1 $P, we get a stack leak. And we can also see 9 down here has a libc leak. So I grabbed those 2 values out. And that's what I use for my libc leak and my stack leak. So you can see %1 and a %9. So I grab those out. We calculate the base of libc, we calculate the return address, we calculate the I address. And so now we know where all those different things are on the stack. Like I said, then we're going to set I to a large negative number, very similar to what we did. We're going to grab that I address. We're going to do the 3rd byte because we want to set that high bit. We grab out what that address is. And remember, we're doing a stack pointer to a stack pointer. So we're going to assign that first stack pointer, and so that it references the second stack pointer so that it points to I. And then we write that high value to I. So cool. Now we get to do a whole bunch of printf exploits. We're going to generate some ROP code, nothing special. We're doing ROP raw. I think there was some alignment issue or something. We're going to call system with bin shell, and we generate our chain. I looked at one gadget. It didn't work though. We can delete this. From there, like for every byte in the ROP code, we're just going to take the next byte that we need to write. We're going to increment that pointer to a pointer up by 1, and then we're going to write that value. For some of them, when setting a null byte, it's a little bit weird. You can't do %0c. I think printf gets a little mad. So if we're supposed to write a null byte, I don't do anything special. I just do a %55. I just write a 0 to that spot. Otherwise, I do a %c. That's why 0 is special cased. Because if you do a %0c, I think printf got mad. But we write out literally byte by byte by byte. And at the very end, when we're done, we go back to the I variable, and we set it to some large value or a small value. I set it to 0, so we write 0 where it was, so it's going to be a large positive value. And then we continue, and we should just get shell. I think this code isn't the most reliable. Python 3, solve that pi. So we'll probably have to run it a couple of times. Oh, we don't. Ran the first time. Sweet. Although I think this is local. Let's see if remote works. We'll get rid of that. Get rid of that. At least we got shell locally. Let's try running it remotely. Hopefully the servers are still live. They must be because we got leaks. We can see this leak looks good at least. A little slow though. Maybe I can set, let's set this to debug and try again. Make sure we're not hooked on something. Oh no, we got to end a file. It's doing a bunch of stuff. Oh, there we go, and it worked. Cool. So we'll cat out the flag. And that was the challenge. So pretty cool, a little bit involved, but a lot of just good techniques to learn. The last challenge is noleek. It said my code had a couple of pesky format string vulnerabilities that kept getting exploited. I'm sure I'll fix it myself if I compile with revro and take away output. We're given source, Docker file, binary, and a netcat port. It's nice of them to give us source. What makes this challenge pretty fun is we get to exploit 2 printfs, or we get 2 printf exploits, but they write not to standard out, they write to dev null, so we don't get to see the response, which is pretty fun. And yeah, that's pretty much all it says, is we get 2 printfs and they write to dev null. Like I said, I didn't solve this challenge, but thankfully the author gave us a write-up, and the write-up is very small. We just need to send these 2 things. And so the trick behind exploiting it is, like I said, is this % or this star operator. So if we read this, there's 3 different printf things. There's this, which is going to write 65,000 bytes. This can be a P or a C, it doesn't matter. So it's going to write 65,000 bytes. Then what this %*13$p is going to do is it's going to take the 13th variable on the stack, and it's going to write out that variable, that many bytes, sorry. So it is a width character that depends on the variable on the stack. So you can do like a dynamic width, which is crazy. I didn't know this existed. So you can do a dynamic width. So far, if we execute both of these, it'll write whatever this value is on the stack and add this many bytes, and it'll write the last 2 bytes to this address in the stack. And so what this is this is going to be a pointer to a pointer again, same as the last challenge. And it's now going to point this pointer to the return address. Cool. And then doing the same sort of exploit, they're going to write a 1 gadget, I think. Yep, they're using a 1 gadget. So they're going to write a 1 gadget. And to do that, they still don't know where libc is, but they're going to take libc. So this is going to be a stack pointer, so they're changing stack pointers. This one must be a libc pointer. So they know that there's a libc pointer at address 12, and it's some variable that they calculated the offset to. They then calculated the offset between that one and the 1 gadget. And they know that if you write this value out, so 67,000 bytes, and then that value, that stack address with the dynamic width at location 12, they then store that into the return address. And so when you return from the function, your 1 gadget will execute, and from there you just get shell. So really fun challenge. I like how it's so small. It's just these 2 little lines, but you know, I think a lot of work went into creating these 2 lines, but pretty fun challenge. And that was all the challenges. If anyone has any questions, please let me know. You can put it in the comments below or message me on Discord. I'm always happy to chat. And thanks to Ångstrom organizers for creating all these fun challenges. And I will see you at the next CTF. Cheers.